This call is now being recorded. Okay, so last meeting we discussed about the Cramerau inequality. We have here in theorem 7.3.9, which says that let x sub 1 up to x sub n be a sample with PDF uh, f of the sample given our parameter theta, and let w of x, which is a function of our sample, be any estimator satisfying these two conditions. We call this the regularity conditions. The first one, we have the derivative of the expectation or the mean of the estimator w of x with respect to d theta is equal to the integral of the partial derivative of the product w of x and then the joint density on the integrals on the overall the sample space dx, and then the variance of our estimator w of x is finite. If these two conditions are satisfied, then the variance of our estimator w of x is greater than or equal to this fractional expression, in which the numerator is the square of the derivative of the mean of our estimator w of x with respect to theta, divided by the mean of the square of the partial derivative of the log of our density with respect to theta. So the fractional expression on the right-hand side of our inequality is called the Cramerau lower bound. Okay, and the proof for this, we use the Cauchy-Schwarz inequality. And then corollary to the theorem, we have the Cramerau inequality for uh, independent and identically distributed case. So if the assumptions of the theorem 7.3.9 are satisfied, and additionally, if the x sub 1 up to x sub n are IID with the given PDF f of x given our parameter theta, then the variance of our estimator w of x is greater than or equal to, okay, we have the same numerator, the square of the derivative of the mean of our estimator w of x with respect to theta, this time divided by n times the expectation of the square of the partial derivative of the log of the density or the PDF f of x given theta with respect to theta. So the difference between the two in the corollary, we make use of the log of the joint PDF, while here we have the log of the PDF of our uh, random sample. So the quantity or the expression in our denominator uh, in the theorem, no, in the theorem, which is actually the expectation of the square of the derivative of the log of the joint PDF with respect to theta, will be called the information number or the Fisher information of the sample. We have an example here illustrating our theorem. Okay, illustrating our theorem, we have the assumption that it satisfies the regularity conditions. Okay, so we're able to compute for the Cramerau lower bound for this example using the theorem. And then we have another result. Uh, we have the lemma 7.3.11. If our density, no, if our density satisfies this equality, this is actually true for an exponential family, then uh, an expression, take note, this is an expression in our denominator in the Cramerau lower bound. So we have here the square, the expectation of the square of the derivative of the log, no, the log of the PDF with respect to theta will just be equal to the negative, the negative of the expectation of, we have here the the second partial derivative of the log of our density with respect to theta. Okay, so we have an example here in which we illustrate our corollary 7.3.10 and at the same time lemma 7.3.11. Okay, so we have this result. We use the same example in which we have now we have a random sample coming from a Poisson uh, or with having a Poisson distribution with parameter lambda. Okay, so we have an example here in which we have an unbiased estimator for the scale uniform. So in this case, we apply our theorem, the Craméral inequality theorem, and then at the same time we apply the corollary, no? The corollary 7.3.10, but we cannot apply the lemma for this particular example because the PDF, the PDF of our random sample does not belong to the exponential family. So we just apply the theorem and at the same time the corollary to this. Okay, so we have here the justification that the mean, the mean of the square of the partial derivative of the log of the PDF. Okay, we have that. And since it is this is IID using corollary 7.3.10, so that is equal to n times the expectation of the square, okay, the square of the partial derivative, the log of the density, no, the PDF lang. Kasi IID naman a case. And then after that, we apply what is our density for this particular example, which is equal to 1 over theta. So if we're going to apply the log, then we have here log of 1 minus log of theta quantity square. And then log of 1 is equal to 0. So we are left with negative log of theta quantity square. And then if you're going to yeah, so paano nga ito nakuha to? Part na to? So we have here the derivative of yeah, the square, take the log to yeah. Kalimutan ko tuloy. You're going to apply first the derivative before the square. Akala ko yung square nasa loob. Okay, so we have that. So you take the derivative of the negative log of theta. So we have the negative of 1 over theta, okay, times 1. And then we square that one, so we have that result. Okay, so the Craméral theorem would seem to indicate that if W is any unbiased estimator of theta, so if we have that condition, then the variance of W will be greater than or equal to Take note, if W is an unbiased estimator, then the numerator in our Cramer-Rao lower bound is equal to 1, and then divided by, okay, so divided by, so we have here our denominator. Ito yon. This is our denominator in the Cramer-Rao lower bound, so that's equal to n over theta. Therefore, the variance of our estimator W indexed by our parameter theta is greater than or equal to theta square over n. So our Cramer-Rao lower bound here is theta square over n. Okay, let us continue now. We would now like to find an unbiased estimator with small variance. Now, so smaller variance compared to this variance of the unbiased estimator W. So as a first guess, consider the sufficient statistic. Okay, we have our sufficient statistic Y, which is the largest order statistic, the maximum of all the random variables. So the PDF of Y is, okay, we have here for our PDF of Y, we have the formula in chapter 4, I think, no? A formula for this, we have f of x sub quantity n, say y, this is equal to n factorial divided by n minus 1 quantity factorial. So then we have n minus n factorial. Then we have the PDF for that. And then we multiply by the CDF, f of xy, raised to n minus 1. And then we have the 1 minus the CDF. Raised to n minus n. Okay, so applying this formula, then we're able to get the PDF of our statistic y in that case. Okay, so y here is greater than 0 but less than theta. So if we're going to determine the expectation of y, okay, so supposedly this would be equal to, we have here the integral of y, and then the PDF. So we have here the PDF, n y to the n minus 1 divided by theta to the n. Then we have our indicator function, okay? Pwede na diretso tayo. So we have here dy from 0, okay? From 0 to theta. Okay, simplifying, so we have that results. So if we're going to integrate this, we can verify that indeed we get this answer. This is equal to n y to the n plus 1 over theta to the n, then we have n plus 1, evaluated from 0 to theta. Okay, so this is the expectation of y. So this implies, okay, this implies that our y here is a biased estimator. Okay, so y is a biased estimator. Okay, showing that n plus 1 over n, y is a unbiased estimator. Okay, this is true because if we're going to find the expectation of n plus 1 over n y, this is equal to n plus 1 over n, and then we have here the expectation of y. and this is equal to n plus 1 over n, and then the expectation of y is equal to n over n plus 1. Then you have here theta, and this is equal to theta. So indeed, our expression n plus 1 over ny is an unbiased estimator of theta. And after that, we're going to calculate the variance. The variance, this is also this expression is also an unbiased estimator of our parameter. If we're going to compute for the variance of this estimator, unbiased estimator. Okay, so first quality here by the property of variance. Okay, we have that. Ito, yung first part. And then the second equality here by definition. Okay, by definition. So the variance of y is equal to the expectation of y squared minus the expectation of y quantity squared. Okay. Yeah. And then if we're going to compute for the expectation of y squared, same thing that we method that we have a while ago. So this is equal to the integral of y squared, and then we have your density, n y to the n minus 1 over theta to the n dy, evaluated from 0 to theta. So this is equal to n of y, n plus 2, or rather n plus 1, divided by theta to the n, they have their dy. And if we're going to integrate that, so we have here n y n plus 2 over theta to the n, and you have here n plus 2, evaluated from 0 to theta. Therefore, we have this value n theta squared, okay, over n plus 2. Pwede nyo lang siya i-check. So we apply that here for our expectation, and then simple calculus or algebra lang pala yan. You get the LCD of that, the n plus 2, and then the square of n plus 1, and then you simplify, you will be able to get this answer. Okay, we have another unbiased estimator of our theta in which the variance, okay, the variance of this unbiased estimator, okay, take note of this, the variance of this unbiased estimator, n plus 1 over n times y, which is equal to theta okay, theta square over n times n plus 2. This variance is less than this value, theta over n. But this theta over n is less than the variance of our unbiased estimator W indexed by our parameter theta. Take note that this is our Cramer-Rao lower bound. Okay, that's our Cramer-Rao lower bound. Yan yung nakuha natin based in our theorem and corollary. And now we have another unbiased estimator of our parameter theta, but the variance of this is lesser. No, ito yung variance niya. Lesser than the Cramer-Rao lower bound. Supposedly, yung Cramer-Rao lower bound, siya na yung pinakamaliit. So, this implying that the variance of n plus 1 over n y, which is theta square over n times n plus 2, is uniformly smaller than theta square over n. So this indicates that the Cramer-Rao theorem is not applicable to this PDF. So in general, if the range of the PDF depends on the parameter, then the theorem will not be applicable. This is actually the restriction of the application and usage of the Cramer-Rao theorem. If we're going to look at the PDF, the PDF, the range of the PDF, if it depends on the parameter, then we cannot apply the Cramer-Rao theorem. So a shortcoming of this approach to finding best unbiased estimator is that even if the Cramer-Rao theorem is applicable, there is no guarantee that the bound is sharp. That is to say, the value of the Cramer-Rao lower bound may be strictly smaller. Because it's a lower bound, it may be strictly smaller than the variance of any unbiased estimator. But in our example above, it's not strictly smaller, but we have found a unbiased estimator of a parameter that is actually smaller than the variance, the variance of any unbiased estimator. So in fact, in this usually favorable case of our density being a one-parameter exponential family, the most that we can say is that there exists a parameter or a function of our parameter tau of theta with an unbiased estimator that achieves the Cramer-Rao lower bound. So however, in other typical situations for other parameters, the bound may not be attainable. So these situations cause concern because if we cannot find an estimator that attains the lower bound, so we have to decide whether no estimator can attain it or whether we must look at more estimators. So if we have an unbiased estimator that attains the lower bound, the Cramer-Rao lower bound, then that is actually a best unbiased estimator. But if that unbiased estimator, the variance of that unbiased estimator cannot attain the Cramer-Rao lower bound, then we cannot decide whether that estimator is a best unbiased estimator. So we have another example here, the normal variance bound. Let x sub 1 up to x sub n be IID, normally distributed with mean mu and variance sigma square. And for this particular problem, we're going to consider estimating our population variance sigma square, where mu is unknown. Take note now, where mu is unknown. So the normal PDF satisfies the assumption of the Cramer-Rao theorem. It's because of the fact, that the normal distribution belongs to an exponential family. And at the same time, we can apply 7.3.11. So we have here the second partial derivative of the log of our density. Okay? Ito yun. The second partial derivative of the log of our density, the derivative with respect to sigma square. And this is equal to 1 over 2 sigma to the 4 minus the square of x minus mu over sigma to the 6. So pwede natin yan, dito muna, say this is equal to, we're going to take we have here the second partial derivative with respect to sigma square. And then if we're going to apply the log to our density, so pwede natin simulan the log of the exponential. So we have here negative 1/2 or negative x minus mu quantity square over 2 sigma square. And then we have the log of 1 over, okay, the log of the product is equal to the sum of the logs. So plus, pero the log of 1 is just equal to 0. So we have here minus, okay? So we have minus the log of 2 pi sigma square raised to 1/2. So this is equal to the second partial derivative with respect to sigma square. Okay, this could be expressed as negative x minus mu quantity square. We have sigma square the negative 1 over 2. And then the log, okay, we have here negative 1/2. Then we have times the log of 2 pi plus the log of sigma square. So if we're going to take the derivative of that, the first derivative with respect to sigma square. So we have now derivative with respect to sigma square. So we have positive, okay, x minus mu quantity square, the derivative of that, so negative, negative. So sigma square to the negative 2 divided by 2. And then for the other expression, the derivative of a constant will just be 0, the log. So we have negative 1 over 2 sigma square. Okay? Or this is just equal to the partial derivative with respect to sigma square. We have here x minus mu quantity square sigma square to the negative 2 divided by 2. Then we have 1 sigma square raised to the negative 1, okay, divided by 2. Okay, so if we're going to take the derivative of that, so we have x minus mu square, the derivative, so we have here negative 2. Okay, so we have negative 2 sigma square raised to negative 3, and then divided by 2. Positive sigma square raised to the negative 2 over 2. So ito, this one will cancel out. So we have here x minus mu quantity square minus yan. Then we have here sigma square cube. And then this one we have plus 1 over sigma 2 sigma square. And we have that result. So yung first term, 1 over 2 sigma to the 4. Okay, minus. Okay, so sa denominator tayo ha, nag-evaluate tayo sa denominator. Now the negative expectation of this second partial derivative of the log of our PDF with respect to sigma square, that would be just be equal to, we just substitute the negative expectation of this. Okay, then after that, if we're going to get the expectation here, we have negative 1 over 2 sigma to the 4, and then we have here plus 1 over sigma to the 6. We have here the expectation of x minus mu quantity square.
Look, what's my score? Nothing is done.
Okay, so this one,
and I'm using a thing. I'm using a thing now.
is equal to the variance of x.
I cannot win because of my team.
Okay, so what do we have here? We have a negative 1 over 2 sigma to the 4 plus 1 over sigma to the 6, and the variance is equal to sigma square. So this is equal to negative 1 over 2 sigma to the 4, then plus 1 over sigma to the 4. Well, this is the same as 2 over 2. Okay? Pareho lang naman yan. And we have these results. So negative 1 over 2 sigma to the 4 plus 2 over sigma to the 4. Then we have here positive 1 over 2 sigma to the 4. Okay, so thus for any unbiased estimator W of our population variance, take note, we have an unbiased estimator W. So the variance of our estimator, no? Dapat ganito yon, the variance of our estimator greater than or equal to. So yung expectation natin dito sa itaas, yung derivative pala, no? The derivative of the expectations is it is an unbiased estimator, then the numerator is equal to 1 divided by, okay, divided by the expression that we have in lemma 7.3.11. Itong ka natin, itong nasa baba, no? Itong part na to. Ito. So that's equal to 1.
I did not read it from the little bit. Here now. Oh, you just let them. You can hear now? Yeah. Chumpal. They're not captured now.
May N pala yun. Sa part na yun, we have an N. Okay, so we have an N. Itong part na to. Itong N natin dito. Ito.
You are a monkey. You are a monkey.
We have an N there. Kasi ito yung ating evaluation. We have that N. Dito. Ito yung part.
You just give me some
Ito. So we still have an N there. Para makita lang nyo ba't may N. So we have here equal to N over 2 sigma to the 4. So this implies that the variance of our estimator is greater than or equal to T2 sigma to the 4 over N. Okay? So ito yung ating Cramer-Rao lower bound in this case. In our example 7.3.3, we have...
My thing is so dumb.
Excuse me for a while. So in example 7.3.3, we saw that the variance of the sample square is equal to 2 sigma to the 4 over n minus 1. Take note that our S square here is also unbiased. And since, no? And since the 2 sigma to the 4 over n here, or n minus 1, rather n minus 1, is greater than 2 sigma to the 4 over n. So S squared does not attain the Cramer-Rao lower bound. Okay, so mas maliit la talaga itong Cramer-Rao lower bound. So the estimator, which is the sample variance, it does not attain the Cramer-Rao lower bound. So in this case, so our S square here is not a best unbiased estimator. Because if an estimator attains, no, if our estimator attains the Cramer-Rao lower bound, then that estimator, that unbiased estimator, is a best unbiased estimator. Okay, so we have a corollary here in which we could able to determine, no, which is able to determine the estimator that attains the Cramer-Rao lower bound. That's why we call here an attainment. So we let x sub 1 up to x sub n be IID with PDF f of x given theta, where our density satisfies the conditions of the Cramer-Rao theorem or the regularity conditions of the Cramer-Rao theorem. We let L, which is a likelihood of the function L of theta given our sample x, equal to this the product of the densities f of x sub I given theta I from 1 up to n, denote the likelihood function. If w of x, which is a function of our sample, is any unbiased estimator of the function of our parameter, which is tau of theta, then this estimator W of the sample attains the Cramer-Rao lower bound if and only if, okay, if and only if we have this, the A theta times the quantity, the estimate, no, which actually the value of our estimator, W of x minus the function of the parameter it estimates will be equal to the partial derivative of the log of the likelihood with respect to theta for some function of A theta. So the first factor here is just a function of our parameter, and then we must express it. Ito, an estimator, no, an estimator or the estimate minus the function of our parameter or the parameter, the function of the parameter it estimates. On the right hand side, we have the uh, partial derivative of the log likelihood with respect to theta. Okay, so let us try to find. Dito kasi, itong formula natin dito, sa example 7.3.14, we use the Cramer-Rao theorem. The Cramer-Rao theorem, we have the inequality that the variance of our unbiased estimator is greater than or equal to that Cramer-Rao lower bound. But we were able to determine the variance, no, the variance of our unbiased estimator, W, we have here. That is for any unbiased estimator. And we know that S square is also unbiased. The variance of our sample variance, S square, is greater than compared to the variance of any unbiased estimator. So it does not attain the Cramer-Rao lower bound. Hindi natin nakita kung ano ang estimator natin dito that would attain the Cramer-Rao lower bound using the Cramer-Rao theorem. So paano natin hahanapin yung ating estimator that would attain the Cramer-Rao lower bound? So let's have this example, a continuation of example 7.3.14. Here we have the likelihood function of our parameter, mu, our parameters mu and then sigma square given our sample. So it's equal to the joint density, okay, the joint density. You can verify this one. So we have 1 over 2 pi sigma square raised to n over 2 because this is a joint density. And then e to the negative 1/2, the summation, the finite summation of the square of x sub I minus mu I from 1 up to n divided by sigma square. So if we're going to determine the log likelihood of this, so the log of the likelihood mu given our sample, kasi log likelihood tayo eh, no? Log likelihood yan. That would be equal to. So apply ka ng log on the right hand side. So meron na lang tayo dito, negative the summation of x sub I minus mu quantity square over 2 sigma square. And then the log of 1 over quotient rule. So the log of 1 minus, pero pwede din natin yan, sabihin na the negative, okay, minus the log of 2 pi sigma square raised to n over 2. Or this is equal to, sulat na natin dito, we have the negative summation of xi minus mu quantity square divided by 2 sigma square. Yung second term natin, we have negative n over 2, and then we have log of 2 pi minus n over 2, then we have the log of sigma square. Okay? So yan yung ating log likelihood function. So if we're going to take the derivative of this with respect to our parameter sigma square. Okay? Mu is still unknown, but we're going to estimate it. Ang estimation na to, we're estimating our population variance sigma square. So, ito yung answer. So, kung ito, part na yan, we have here the partial derivative of the log likelihood sigma square given our sample with respect to sigma square. Okay? So, take the derivative. Ito siya. Pwede natin ito ma-express, no? Pwede natin ito the negative summation of x sub I minus mu square. We have 2 to the negative 1. Ayan. Over 2. And then yung negative n over 2 log of 2 pi. And then minus n over 2 log of sigma squared. Dito pa rin yan ha. Ito. Okay, so the negative of negative, so we have positive. So we have positive summation of xi minus mu quantity square. So we have sigma squared to the negative 2 over 2. And then yung second term, there's a constant. So that would be 0. Then we have your negative n over 2, 1 over sigma square times 1. Okay, so we have here summation of x sub I minus mu quantity square divided by 2 times sigma square then minus n over 2 sigma square. Kailangan natin i-express, no? Kailangan natin i-express in this form. Kasi nakuha na natin yung ating partial derivative of the log likelihood function. So, paano natin i-express in that form? We have a of our parameter, and then our estimator minus the function of the parameter it estimates. So, ano yung a of the parameter natin dito? So, in other words, we're going to factor out. Pwede natin i-factor out ang n. Kasi ano yung parameter natin dapat maiwan dito? Dito na case, ang maiwan dapat dito, sigma square. Sigma square, yan maiwan dyan. So we're going to factor out n over 2 sigma square sigma square square. So yung maiwan dyan, so first term natin, we have here the summation of xi minus mu quantity square divided by n. Okay, it's divided by n minus yung sa second term, we factor out n over 2 sigma square square, so may 1 sigma square. Okay, so this, according to our corollary, this is the parameter tau of sigma square Okay, the function of our parameter. And this is our, ito na yung nagre-refer sa atin.
Sir, wala kayong makita, sir.
No, wala.
Yung screen mo, sir.
Okay,
Wala,
so,
ata, sir.
ba't kaya nangyari? Thank you for that, Noli. Hindi ko nakita. Oh, sorry. Join ulit. Oh, saman.
Biasanya kung sa may makapag ko
Ayun, dito na lang pumunta na sa ubay. May klase ko. Okay, share screen. Wala di siya. Okay, so let me go back. In our corollary 7.3.15, we're going to use this corollary in order to determine our estimator that attains the Cramer-Rao lower bound, the Cramer-Rao lower bound. Okay, so we have this. Na-express na natin yung ating partial derivative of the log likelihood. Ito yan. Yung partial derivative ng log likelihood equal to this factor, no? The product of these two. A function of theta, A of theta, and then the second expression should be an estimator, rather the value of our estimator, or sorry, W of x, and then minus the function of our parameter. So in this case, ito yung ating partial derivative of the log likelihood, and then we've expressed it in this form. Kailangan kasi natin dito na part, dapat ito siya would be equal to the function. Yung parameter natin gusto na i-estimate, we have tau square. Parang nag-multiply ka dito ng tau square, rather tau square. Tau of sigma square is also sigma square. Ayan. Sigma square over sigma square. So we can factor out n over 2 sigma square square. So ito ngayon, yung ating function of our parameter, sigma square, ito. Ito ngayon yung ating estimator. Not the estimator, the estimate, the value of our estimator, W of x, kasi small letter man yan, the estimate. And this is our function of our parameter, that is A of sigma square times that minus. Okay? So according to our corollary, ito yung ating estimator. No? Therefore, conclude tayo. Therefore, if we take mu, kasi may summation, may mu na yan. If mu is known, kung alam natin yung ating mu, then yung W of the sample, ano yung W of the sample? Equal siya sa the summation of the random sample xi minus mu quantity square, I from 1 up to n, divided by n. Okay, ito siya, attains. This attains the Cramer-Rao lower bound. Because it attains the Cramer-Rao lower bound, so W of x of this sample is a best unbiased estimator of sigma square. Naintindihan nyo ba? Yung sa previous example natin, ginamit natin yung Cramer-Rao inequality, yung Cramer-Rao theorem. Pero, yes, LJ? LJ, nag-raise ka ng hand?
Wala, sir. Ganyan na, sir. Katong
ganyan.
na-off.
So, using the Cramer-Rao theorem or the Cramer-Rao inequality, any, no? Dito, no? Kuha natin. Any unbiased estimator, itong part na to, the variance of that unbiased estimator is greater than or equal to 2 sigma squared over n. Kung hahanapin natin kung ano yung unbiased estimator that would attain the Cramer-Rao lower bound, nagbigay tayo ng example dito, itong sample square, unbiased man siya, pero hindi naman siya naka-attain ng Cramer-Rao lower bound. So yung sample variance, S square, is not a best unbiased estimator. Kung hahanapin natin kung ano yung unbiased estimator that would attain the Cramer-Rao lower bound, then we're going to use this corollary. Understood?
Yes, sir.
Okay, thank you, Kim. What about the other students?
Yes, sir.
Okay, so let's proceed to the next subsection. We have sufficiency and unbiasedness. Okay, so in the previous section, the concept of sufficiency was not used in our search for unbiased estimates. Itong sinabi niya dito, siguro nakalimutan niya, naggamit tayo ng sufficient statistic when we consider y there, no? Which is actually the maximum order statistic. Like if you can still recall. Ito, kung gusto niyo tingnan, we use the sufficient statistic in this example. Okay, we have here a sufficient statistic y, the largest. And then for this sufficient statistic, we have a function of our sufficient statistic. Ito yun, the function of our sufficient statistic that would result to unbiased estimator of theta. Klaro ba sa ang color niyo na light green sa inyo, Jen?
Okay ra, sir.
Okay, sir.
Okay. Siguro nakalimutan lang dito na part, no? So the concept of sufficiency was not used in our search for unbiased estimates. Pero we have that example that we, from the sufficient stat, then we're able to find an unbiased estimator also, which is a function of our sufficient statistic. So we will now see the consideration of sufficiency is a powerful tool indeed. So the main theorem of this section, which relates sufficient statistics to unbiased estimate, is another clever application of some well-known theorems. So recall from chapter 4 that if x and y are any two random variables, then provided the expectations exist, we have the expectation of the unconditional expectation of x is equal to the expectation of the conditional expectation of x given y. And then the unconditional variance of x is equal to the variance of the conditional expectation of x given y plus the expectation of the conditional variance of x given y. We have this in chapter 4. So we're going to use these tools to prove this theorem. We call this as the Rao-Blackwell theorem, which states that let W be any unbiased estimator of the function of the parameter tau of theta, and let T be a sufficient statistic for our parameter theta, and then we define phi of Take note, this is a function. Okay, red na lang. This is a function of our sufficient stat. So phi of t, which is a function of the sufficient stat, is equal to this conditional expectation of the unbiased estimator condition on the sufficient stats. We define that. Then it says here that the mean, parang sinasabi na lang natin, the mean of the random variable, because this is a function, the function of our sufficient stat, the mean of phi of t indexed by our theta will just be equal to the function of our parameter. So, ang implication yan, no? Kung totoo nga ito pag-define natin, then the mean of our function of the sufficient stat equals siya sa the function of the parameter. So that would mean that our phi of t is also an unbiased estimator. Take note, W lang yung unbiased estimator. Meron tayong sufficient statistic na t. Tapos, dinefine natin na ang phi of t, which is a function of the sufficient stat. Pag kunin natin yung mean ng phi of t, equal siya sa tau of theta. So that means that phi of t is also an unbiased estimator of tau of theta. And it says here that the variance of phi of t is less than or equal to the variance of W. That is, W, take note, W is for any unbiased estimator. So the variance of W for all theta in the parameter space. So meron tayong nakita, no? Meron tayong nakitang unbiased estimator. This unbiased estimator is a function of our sufficient stat that is uniformly better unbiased estimator of our function of the parameter tau of theta. Yung sa example natin kanina, no? Nakita man talaga natin na yung variance is smaller than the Cramer-Rao lower bound. Supposedly, kung lower bound na yung Cramer-Rao lower bound, yung example natin kanina, wala na dapat pang variance dun na mas maliit sa kanya. So in this case, no, sa Rao-Blackwell theorem, we were able to find an unbiased estimator that would be less than or equal to the variance of any unbiased estimator of our function of the parameter tau of theta. Okay. Okay. Sandali lang guys ha. Check ko muna kung pumasok na ba yan. Yahoo. Ay, kasi ko pa na-send. Sandali lang. A moment now. A moment please. Compose over STAP 332. We attach from file. Then we have 332. A few moments. Sandali lang. import. Lagyan natin ng pa. 1. Import. One. Duplicate. Okay, so we have here the Rao-Blackwell theorem, uniformly better. So we have here the proof for that. From 7.3.13, we have here the function of our parameter tau of theta. Since W here is an unbiased estimator, so the mean of W will be equal to the tau of theta. And then using the 7.3.13, so the unconditional expectation will just be equal to the expectation of the conditional expectation of W given T. No? This is our sufficient statistic. This is our unbiased estimator. And we define this expectation, conditional expectation of W given T is equal to a function, a phi of T, function of our sufficient stat. Okay, so we have proved this. Okay, diretso na. And the next, show that the variance of phi of T is less than or equal to the variance of W. So we have the variance of W according to 7.3.13 equal to the variance of the conditional expectation of W given T plus the expectation of the conditional variance of W given T. Okay, we have that. And then yung variance natin, ito kasi, this is just equal to phi of T, so that's the variance of phi of T. And then we retain the second term. So nakita natin dito na ang variance of W is equal to the sum of these two terms, the variance of phi of T plus the expectation of the variance. Since we know that the variance is always positive, then the mean of that, the variance of the conditional, or the conditional variance of W is positive. So the expectation of that will also be positive. Therefore, the variance of W is greater than or equal to the variance of phi of T. Hence, yung function of our sufficient stat is uniformly better than any unbiased estimator W. So it remains to show that phi of T is indeed an estimator. Now, if indeed an estimator, that is, we must show that phi of T, which is equal to the conditional expectation of W of T, is a function of only the sample. It does not depend on our parameter because it's an estimator. So, but we have a following, an example later showing that it says here, but follows from the definition of sufficiency and the fact that W is a function only of the sample, then the distribution of the conditional distribution of W given T is independent of theta. Hence, phi of T is uniformly better, unbiased estimator of the function of the parameter tau of theta. So therefore, conditioning, take note, conditioning any unbiased estimator on a sufficient stat, gaya nito, conditioning any unbiased estimator on a sufficient stat will result in a uniform improvement. So we need consider only statistics that are functions of a sufficient statistic in search for the best unbiased estimator. But in identity 7.3.13, it make no mention of sufficiency. So it might at first seem that conditioning on anything, any statistic, not necessarily a sufficient statistic, will result in an improvement. So this is in fact true, but the problem is that the resulting quantity will probably depend on the parameter and not be an estimator. So yung resulting na masatisfy niya to, na it would estimate our function of the parameter, that the variance of that is still greater than the variance of phi of t is still greater than the variance of any unbiased estimator, but phi of t there is not an estimator because it depends on the parameter. Let's have an example to illustrate that. No, conditioning on an insufficient statistic. Hindi siya sufficient statistic, but i-condition natin siya. Example, i-condition natin siya in an insufficient statistic. So let x sub 1, x sub 2 be IID, normally distributed with mean theta and variance 1. And then the statistic, the sample mean, we have 1/2 x1 plus x2 has. So the mean of the sample mean is equal to the population mean theta. The variance of the sample mean is equal to 1 over sigma square over n. In this case, yung sigma square natin, yung population variance is 1, so 1 over n, which is 2, so 1/2. Okay, the variance is equal to, the variance of the sample mean is equal to 1/2. So consider conditioning on x sub 1, which is not a sufficient statistic. Okay, we condition it. So we let phi of 1 be equal to, that's how we define it using our theorem, the Rao-Blackwell theorem. So that's the conditional expectation of our unbiased estimator, di ba? Unbiased ito. Patong kanina W yun kasi unbiased. Alam natin na ito because the expectation of x bar is equal to the parameter it estimates. Unbiased ito, itong unbiased. It's an unbiased estimator. So condition that this time this is not a sufficient statistic. Okay, so it follows from 7.3.13, okay, that the mean, okay, the mean of phi of 1 is equal to theta. Parang hindi masyadong clear sa expression na yan, no? Parang sabihin natin na yung phi of x1 is unbiased estimator of theta. So pwede natin, we have here theta is equal to the expectation of the sample mean because it's an unbiased estimator indexed by theta. Okay, and then using the identity, the unconditional expectation is equal to the expectation of the conditional expectation of our sample mean given x sub 1. Okay, we have that. That's conditional. And this is equal to the expectation. Here we have defined that this is equal to phi of x1. Okay, that is why, totoo yun. The expectation, lagyan natin ng theta dyan. The expectation of phi, so totoo na to, yan. So, parang mahirap minsan kung we start, no? Ayan yung justification yan. Next, what about the variance of phi of 1? Sabi dito, the variance of phi of 1 is less than or equal to the variance of the sample mean. Kung titingnan natin sa Rao-Blackwell, totoo nga, nagsatisfy siya. So, ibig ba sabihin na that phi of is better than, so phi of is better than phi of 1? So, itong phi of 1, kwan ba siya? Is it an estimator? Because when we say it's an estimator, it should be a function of the sample. It does not depend on our parameter. It satisfies also this one. So, paano natin yan i-verify? Now, variance of phi of x1 is less than or equal to the variance of the sample mean. Pwede natin dito, say the variance of phi of x1 indexed by theta. Okay? So, ano yung phi of x1 natin? So, that's actually the variance. Ito yung phi of x1 natin. So, the variance of the conditional expectation of x bar given x1. Okay. So, the variance of the expectation, the variance of the conditional expectation will just be equal to the variance of x bar, okay, minus the mean of the conditional variance of x bar over x1. Okay? So, dyan natin na malalaman na itong variance ng phi of x1 is less than or equal to. Mas maliit kasi siya. Ito. Variance of x minus, may minus pa siya. So, variance of x bar rather. Okay, so we have that. Itong part na to, ginamit pa rin natin yung 7.3.13. Pero, parang tinranspose natin ito, no? Tingnan natin ito man yung given. So, ito siya, tinranspose natin dito sa kabila. Maging minus siya. Okay. Yan ang result niya. So, we have verified that the variance, parang mag-conclude kaagad kayo na ang phi of x1 is an estimator. So, phi of x1 is better than the sample mean, but let us try to check if indeed phi of 1, ba siya? Estimator ba siya o hindi? So, what is phi of x1? Phi of x1, we have here the conditional expectation of the sample mean given x sub 1. Okay, so ano yung kanyang ano yung conditional expectation natin dyan? Pwede natin, after this, para maklaro yan siya, na part, para nakuha yan, that's actually the expectation. Okay, ano yung ating sample mean? We have 1/2 x1 plus x2 given x1. So using the property of expectation, the expectation of the sum will just be equal to the sum of the expectation. Okay, ito yung result. So 1/2 the expectation, conditional expectation of x1 over x given x sub 1 plus 1/2 the conditional expectation of x sub 2. Okay, klaro na itong step na yan. And then here, the conditional expectation of x sub 1 given x sub 1 will just be equal to x sub 1. And then in this case, the conditional expectation of x sub 2 given x sub 1 is equal to the unconditional expectation of x sub 2. That's by independence. Okay? IID tayo. Itong part na yan. IID. By independence. So if we're going to look at our function, the function of a statistic, x1, but this statistic is not sufficient stat. The function of that, it depends on our parameter theta. Hindi lang siya, it depends on the sample, but it also depends on the parameter theta. So, yung ating phi of x1 is not an estimator. Kaya, hahanapin talaga natin yung sufficient statistic. And the function of that sufficient statistic will give us, no? Itong tao sabi niya, will give us an improvement and would help us determine the best unbiased estimator. Example lang yan. We know now that in looking for a best unbiased estimator of the function of the parameter tau of theta, we need to consider only estimators based on a sufficient statistic. The question now arises that if we have, if the mean of phi is equal to tau of theta, supposedly, para klaro yan, is the mean of the function of our statistic, sufficient statistic, is equal to tau of theta. Parang ganun yan. And theta is based on the sufficient statistic. Yan sabi na. Theta is based on the sufficient statistic. Then, the conditional expectation of phi of t given t will just be equal to phi. Itong part na to, sabihin natin yan, the expectation of phi of t given t. Supposedly, ganun yan. Will be equal t will be equal to phi of t. Conditional. So how do we know that phi is a best unbiased, or phi of the sufficient stat? Itong sinasabi nito. It's a function of a sufficient stat. How do we know that phi is a best unbiased? Of course, if phi of t, parang ito na, phi of t, phi of the sufficient stat t attains the Cramér lower bound, then it is best unbiased. Kung nakuha niya, accurate siya doon sa Cramér lower bound. So it is a best unbiased. But if it does not, have we gained anything? For example, if we have a phi star, another unbiased estimator of a function of a parameter tau of theta, how does phi star, conditional expectation of phi star of t compare to phi? So the next theorem answers this question in part by showing that a best unbiased estimator is unique. Okay, so we have here, if W is a best unbiased estimator of the function of the parameter tau of theta, then W is unique. We have this theorem. So to see when an unbiased estimator is best unbiased, we might ask how we could improve upon a given unbiased estimator. Suppose that we have W that satisfies. Okay, so this is an unbiased estimator of the function of the parameter tau of theta. And then if we have another estimator U that satisfies that the mean of U is equal to 0 for all theta in our parameter space, pag ito siya mag-satisfy, then U is an unbiased estimator of 0. Ito yung definition niya, no? It's an unbiased estimator of 0. Then the estimator phi sub A, okay, phi sub A, which is equal to W plus AU, where A is a constant, will satisfy, okay, it will satisfy that the mean of phi sub A, equal to the function tau of theta. Ibig sabihin na ito, unbiased estimator of tau of theta. Alam naman natin yan. Kung titingnan natin, kung i-verify natin, ano yung, ano itong, get the expectation of that? W plus AU. So we have here the expectation of W plus A times the expectation of U. So here, this is tau of theta because W is an unbiased estimator. But this one, the expectation of U is equal to 0. So the whole term will just be equal to 0. Okay, that's imply also an unbiased estimator of tau of theta. Okay? Totoo. Ang tanong ngayon, sino yung better na estimator? Yung phi sub A or yung W? Na yung phi sub A, which is now being expressed as W unbiased estimator plus AU. So, can phi of A be better than W? So, titingnan natin. Pareho lang naman yung kanilang mga unbiased estimator naman ito sila. So, we're going to check their variances. So, check the variance. So, the variance of V of A, the variance of W plus AU, just substitute it and apply the definition of the variance or property of the variance. So, we have here the three terms. Variance of W plus 2A, the covariance of W and U, plus A squared, the variance of U. Property yan ng ating variance. Now, if for some theta equal to theta sub 0, the covariance of W and U is negative, because we know that the covariance of two random variable, it could either be negative, it could either be positive, pwede din maging 0. So if it is negative, then we can make this expression here to be less than 0. To be a negative value. Para ma-negative siya, para this one will be a better estimate by choosing that one. Okay, choosing. Hence, a phi of A will be better than W at theta is equal to theta sub 0. Because we choose. Pwede naman, no? And W cannot be best unbiased. Kasi meron tayong unbiased estimator na mas maliit yung variance niya. So a similar argument will show that if the covariance of W and U is positive for any theta sub 0, then W cannot be the best unbiased. We have that in exercise 7.53. Thus, the relationship of this unbiased estimator W with this time, the relationship with the unbiased estimator of 0 is crucial in evaluating whether W is best unbiased. So this relationship, in fact, characterizes the best unbiasedness. So we have this theorem. If the mean of W is equal to tau of theta, that means unbiased estimator in W, ito siya is the best, na siya, no? It is the best unbiased estimator of the function of the parameter tau of theta if and only if. So we have a biconditional statement here. If W is uncorrelated with all unbiased estimator of 0. Because if W is uncorrelated with all unbiased estimators of 0, then the covariance is equal to 0. Ito, equals to 0 yan siya. Uncorrelated. So, yung variance ng phi, kasi 0 na ito. Yung covariance of WU, dito tayo, tumitingin tayo dito na part. Ito. 0 na yan. So, yung variance ng phi of A is greater than yung variance ng W. That is why we can say that the variance or the W is the best unbiased estimator of tau, function of our parameter tau of theta. Okay, so although we now have an interesting characterization, interesting masyado, characterization of best unbiased estimators, its usefulness is limited in application. We have a remark here. It is often difficult task to verify that an estimator is uncorrelated with all unbiased estimators of 0. Solving for the covariance, no? But it is usually difficult to describe it, no, all unbiased estimator of 0. How can you describe the all unbiased estimator of 0? However, it is sometimes useful in determining that an estimator is not best unbiased. So we have an example here, unbiased estimator of 0. Illustrating, no? Parang counterexample. Let X be an observation from uniform 0 to theta to theta plus 1 distribution in this case. So alam natin na yung ating density niyan would be equal to 1 over theta plus 1 minus theta. So 1 lang yan. 1. But our X here, theta plus 1. Okay, we have that. 1. And pwede natin i-solve yung kanyang CDF. That's equal to X. Ganun din. Theta. Theta plus 1. If we're going to compute for the mean, kung gusto nyo alam nyo kung uniform siya, meron naman tayong formula niyan kaagad. So ano yung mean of X? Pwede yung mean of X natin. The mean of X, using our formula, that's actually A plus B. Yung A ito, B. No? A plus B over 2. So parang ito, theta plus 1 over 2. So we have here theta plus 1/2. O ito, answer na, theta plus 1/2. Ito, ang ginamit niya, we apply the definition of expectation. The definition of expectation, this is equal to the integral of X 1 naman yung density natin. So may indicator function lang tayo dyan of x on the closed interval theta to theta plus 1 dx. Negative infinity to positive infinity. Apply yung indicator function natin. Ito yung result. And then, that's actually x squared over 2 evaluated from theta to theta plus 1. Okay, so yan yung result natin. And then yung variance of x equal to 112. It's easy to check. Pwede pag-solve ng variance, solve mo muna itong expectation na x squared minus the mean of x. Nakuha naman natin ito. Ito na lang. Ito rin gamitin natin. Meron na tayong x squared. No? Parang the integral from theta to theta plus 1. X squared dx. Yan. Minus the second term na yan. Then we have here 1 over 12. Or, may formula naman tayo sa variance. Check natin ha. Narinig yung ulan?
Yes, sir. Pasok tayo.
Meron siyang noise cancelling. Okay, so, or pwede natin isolve yung variance of x using the formula. We have actually b minus a quantity square over 12. So, ano yung b minus a? Theta plus 1 minus theta over 12. Okay? So, 1 over 12. Satisfy pa rin natin ito. 1. Or, pwede ito, no? Pwede ito yung paggamit niya to verify. So, for this PDF, unbiased estimator of 0 are periodic functions with period 1. With period 1. Guys, naririnig nyo ba ang ulan?
Wala naman, sir.
Okay lang sa inyo ha din ha. Kay dili kayo masamok. Pero ako kusog ang tingog kay panako ang noise cancelling. Naman noise cancelling so hindi maganda. So for this PDF, unbiased estimator of 0 are periodic functions with period 1. Murag lisod na ni siya nga i-explain, no? Unbiased estimator of 0 are periodic functions with period 1. This follows from the fact that if h of x satisfies this, ano nga yung ating unbiased estimator of 0? That means the expectation of this unbiased estimator will be equal to 0. So, ang ibig sabihin yan, the expectation of h of x, okay, will be equal to 0. Kaya ito ngayon yan. So, that's the, ano yung h of x natin? H of x. So, we have that. So, x, alam natin na x uniform. So, that's actually the integral of h of x. Then the PDF, no, the PDF of the uniform, 1. So, 1. Naintindihan nyo ba ito? Kung part na to? Ba't diretso ka agad? Supposedly, yung mean of x natin yan. So, by the definition of expectation, kasi h of x. So, ano yung density ng x? 1. 1 times the indicator function of x on theta plus 1 dx. From negative infinity to positive infinity. Kaya ito yung result agad. Ito na sa itaas. Equal to 0. Because we want to find the unbiased, unbiased estimators of 0. For all theta. Take note, that is for all theta. Meron ako nakalimutan dito na part. Ito, hindi ko na And so, x minus 1/2 is an unbiased estimator of theta. Take note, ito ang implication dito that the mean of x is equal to this. So this implies that x is a biased estimator. So kung x biased estimator, so yung x minus 1/2 is an unbiased estimator of theta. Okay, it's an unbiased estimator of theta. Pwede naman natin ito mag-verify. So an expectation of x minus 1/2, so that's parang ma-verify natin the expectation of x minus 1/2, so that's equal to the expectation of x minus 1/2. So that's equal to theta plus 1/2 minus 1/2 equal to theta. So unbiased estimator siya. So it's easy to check that the variance of x is 1/12. Pero ang inire-refer nito, hindi talaga yung variance of x. Parang nakalimutan ko. It's referring to the variance of x minus 1/2. So the variance of x minus 1/2, according to our property of the variance, it will just be equal to the variance of x. Understood? So ito ngayon, ibayin natin yung color, dark green. Ito, sobra naman. Orange na lang. Ito, unbiased estimator. Tapos, dahil dito, no? Tapos yung variance nitong unbiased estimator is equal to 1/12. Yan yung hinahanap natin. Ito yung mean, unbiased estimator siya, yung band. Okay. Yan yung gusto ko i-emphasize pala dyan. Hindi yung variance ng x lang. The variance of x minus 1/2. Okay, so next. Then we have this equality here. Itong part na to, medyo, yung zero dito is actually equal. Ito, 0 equals, follow ka ganyan. Yung 0 is equal to the derivative with respect to theta of 0. Okay? So ano man yung 0 natin? Ito yung 0. Ito yung 0. So the derivative with respect to theta of 0. So ano yung 0? Equal to that integral. Ito yung 0. Tama po ba? Yan yung 0. Parang nahuli. Nahuli siya. Wala pa. Humihina ang internet. Guys, can you hear me?
Yes, sir.
Hindi pa nag-reflect yung naisulat ko. Okay yan. So yung 0, ito yung 0, no? Ito yung 0. So substitute na natin yung 0. That's the integral. And then if we're going the derivative of the integral, pwede na i-evaluate ka agad. That's h of theta plus 1 minus h of theta. So ibig sabihin na kaya itong sabi na the PDF is unbiased estimator of 0 are periodic functions with period 1. So kailan mangyayari ito? Itong part na to, this is of period 1. Period. This is of period 1. Since, no? Ang difference nito, theta plus 1 minus h of theta equal to 0. Yan, dito yung 0. Period 1. So, how are we going to choose our function h of x now? That will be the sine 2 pi x. Kasi kung ito yung ating okay lang guys na lampas tayo. Oras. Lampasan na to. May klase ba kayo?
Okay na po.
Okay. So kunwari ito yung ating okay, this is 0 radian, pi over 2 radian. pi radian. This is 3 pi over 2 radian. This one will become 2 pi. Balik naman siya sa 2 pi. Kung titingnan natin dito, if we're going to divide it into 8 parts, so this is 1 over 8 pi, 0 over 8 pi, so 0 over, and then this one 1, 1 over, so this pi over 4, okay, no? 2, so pi over 4 radian, 2 pi over 4, okay, that's 2 pi over 4, so pi over 2, then you have 3 pi over 4 radian, 4 pi over 4, so that's 5, then we have 5 pi over 4 radian, and then we have 7 pi over 4 radian. Pwede din yan, no? Say in pi over 6 and then pi over 3. Pero alam natin na, say for example, for this particular case here, okay? Kung ito yung angle natin, okay, that's referring to theta here. This is theta. Na period 1 man tayo. Pero yung value ng sine pi over 4 would be the same as this. One rotation, then pabalik, balik siya ulit. That would be the same. So with period 1, pwede naman yun i-graph natin, no? Yung sa graph kung x and y natin yan, meron tayong wave, no? Sine wave. Okay, so our function here, we choose the sine of 2 pi x. Now if we're going to compute for the covariance, ito na ngayon yung mas importante. Ano nga yung covariance natin? Yung covariance ng W, unbiased estimator. So this is the unbiased estimator of our function of the parameter. Okay, this is the unbiased estimator of the function of the parameter. Estimator of the function of the parameter, tau of theta. So in this case, that's actually theta. Ang tau of theta natin. Itong pangalawa, this is the, what we call, the unbiased estimator of 0. Kasi totoo ito, yan. Unbiased estimator of 0. Ito, sine of 2 pi theta. H of x is sine 2 pi of x. So this is the unbiased estimator of 0. So pag ang covariance ng unbiased estimator of function of the parameter and then the unbiased estimator of 0, kung 0 siya, no, kung 0 siya, then the variance of the unbiased estimator, itong x minus 1/2 is smaller, no, than the variance of phi of a, yung kanina, according to our definition. Pero dito, kung titingnan natin yung covariance nito, titingnan ba natin kung value dito equal to 0? So the covariance of x, okay, we have here, according to our property of covariance, no, the covariance of x minus 1/2 sine of 2 pi x is the same as the covariance of x sine 2 pi x. That's the property of covariance. And the next, it is equal to, yan, equal. Pero yung covariance ng x sine of x, by definition, that's the expectation of x, and then sine of 2 pi x, and then minus the mean of x, and the mean of sine 2 pi x. Diba? Yung covariance ng x and y is equal to the expectation of xy minus the mean of x, the mean of y. Yan yung formula natin. Pero ano yung mean? Unbiased estimator of 0 man ito. So the whole thing will just be equal to 0. unbiased estimator of 0. So the expectation of sine pi of x will just be equal to 0. So the whole term will just be equal to 0. So ito ngayon, we do have that by applying the expectation. So x sine of 2 pi x dx evaluated from theta to theta plus 1. And then we have this. We apply integration by parts here. Yung integration by parts, the integral of u dv is equal to uv minus the integral of v du. So in this case, ito yung u, ito yung u, ito yung dv. So ito yung u, ito yung v. Alam natin yung v. We have that. Integration by part. And then integrable na ito, part na yan. So we have that result. And we see that the covariance of x minus 1/2 and then sine 2 pi of x is not equal to 0, which is the negative of cosine 2 pi theta over 2 pi. So we use the identity here. So hindi, ang ibig sabihin yan na correlated yung ating unbiased estimator of the function of the parameter tau of theta correlated with the unbiased estimator of 0. So hence, no, n cannot be. So this one, unbiased siya, it cannot be a best unbiased estimator of theta. Kasi kung 0 yung covariance natin, then the x minus 1/2 will be the best, it's the best unbiased estimator of our function of the parameter. Okay, so tapusin ko na lang ito ha. Medyo mahaba-haba pa pero ito, hindi man tayo nagklase last meeting kasi. Okay lang ba sa inyo? Hello?
Yes, sir.
Okay lang.
Okay ra, sir.
So to answer the question about the existence of a best unbiased estimator, what is needed is some characterization of all unbiased estimators of 0. So given such characterization, we could then see if our candidate for best unbiased estimator is in fact optimal. But characterizing the unbiased estimator of 0 is not an easy task and requires conditions on the PDF or PMF with which we are working. So note that thus far in this section, we have not specified conditions on PDFs. So the price we have paid for this generality is the difficulty in verifying the existence of the best unbiased estimator. So if the family of PDFs or PMFs has the property that there are no unbiased estimators of 0 other than the 0 itself, then our search would be ended. Since any statistic W satisfies the covariance of the unbiased estimator, ito yung unbiased estimator of the parameter, function of the parameter. Ito yung unbiased estimator of 0, which is actually the 0 itself. Yung covariance is equal to 0. Then, no, it says here, we'll be able to determine the best unbiased estimator. So recall the property of completeness defined in definition 6.1.4. Hinahanap ko ito sa book mo, saan itong 6.1.4. Parang mali yata. Ito yung nakita ko na definition, 6.2.21. Talking about completeness of the family of PDFs. So, parang nilitan ko lang para ma-recall natin. So, if f of t be a family of PDFs or PMF of our statistic t of the sample, then the family of probability distribution is complete if the expectation of g of t is equal to 0. So, ibig sabihin nito, this is an unbiased estimator of 0. Yung g of t, yung g of the function of the statistic t is an unbiased estimator of 0. Kaya ito ngayon, may unbiased estimator of 0 tayo. By the way, itong other than 0 itself, ang nire-refer niyan, we have the 0 function. The 0 function which is this, no, the function of our sample, yung answer niya is always equal to 0. Yan yung nire-refer niya. Kaya ito, function ito, or random variable. That refers to the zero random or the zero function. Na yung image niya is always 0. So it's a, then equivalently, complete yung ating family of PDFs. Then yung T of X, the function of our sample is called a complete statistic. So may relationship yung completeness of the family of distribution and the completeness of the statistic. Ito yung example, na-discuss ko naman yan. Last two examples na tayo. Two examples and one theorem. So continuation. Okay, for x1 up to x sub n, IID uniform. Okay, IID uniform. We have this in our previous example. Na-review ko a while ago. So this is actually, no, ito yung ating sinatawag na sufficient statistic na y. But n plus 1 over y, n plus 1 over n times y, it's an unbiased estimator of theta. So this is a function of our statistic y, where y is the maximum order statistic. Okay, so the conditions of the Cramer-Rao theorem are not satisfied. Because, bakit nga ito hindi nag-satisfy yung Cramer-Rao theorem? Because the range of the PDF, the range of the PDF depends on the parameter. So the Cramer-Rao theorem is not applicable to this PDF. Hindi man natin ma-express din yung ating PDF into an exponential distribution. So it's not, and we have not yet established whether this estimator is best unbiased. And then in example, in the previous chapter, 6.2.23, however, we have shown that y, we have shown this is a complete sufficient statistic. It's a complete sufficient statistic. So this means, this according to the definition, we have shown that y here is a complete, according to this definition. Pwede nyo yung balikan, is a complete sufficient statistic. So this means that the family of PDFs of y is complete. So if it is complete and there are no unbiased estimator of 0 that are based on y. No unbiased estimator of 0 that are based on y. Therefore, yung n plus 1 over n y here is uncorrelated with all unbiased estimators of 0. So the covariance of n plus 1 over ny and then the 0 function is equal to 0. And thus the n plus 1 over n y is the best unbiased estimator of our parameter theta. So ginamit natin yung completeness na definition. We usually apply the definition, say, if we cannot express yung ating PDF in an exponential form. Alaman natin na ito, yung PDF nito, yung uniform, cannot be expressed in the exponential, ano nga yung ko natin? In an exponential family. So ginamit natin yung definition for the completeness of the family of distributions. Okay, so we sum up the relationship between completeness and best unbiasedness in the following theorem. So let T be a complete, take note, no? T here is a complete sufficient statistic for the parameter theta. Sufficient pa siya, complete pa siya. And then phi of T be any estimator based only in the complete sufficient statistic. Kanina, yung previous example natin, we just have considered the sufficient statistic, the function of a sufficient statistic. But this time, a function of a complete sufficient statistic, phi of T. Then phi of T is the unique best unbiased estimator of its expected value. Ano nga ibig sabihin niyang the best makita lang natin yan the last example. Let T be a complete sufficient statistic for a parameter theta, and let phi of T be an estimator based only on this complete sufficient statistic. Then this function of the complete sufficient statistic is the unique best unbiased estimator of its expected value. So let's have this last example, binomial best unbiased estimation. So let x sub 1 up to x sub n be IID binomial coming from a binomial distribution with k number of success and the probability k number of trials and the probability of success theta. So the problem is to estimate the probability of exactly one success from a binomial distribution with k number of trials and probability of success theta. That is, we're going to estimate tau of theta. Ano yung tau of theta? Exactly one success. So the probability that x is equal to 1. Ito. X is equal to 1 success lang. Kasi yung binomial natin, no? Referring to the number of successes. Binomial distribution or random variable referring to the number of successes. If we have only one success, so the probability that x is equal to 1, and then we have here, okay, and that's actually a combination of k taken 1, the probability of success raised to 1 minus the probability of failure, k minus 1. So that's our function of our parameter. This is what we're going to estimate. Now, the summation of x sub I from 1 up to n, you have learned this in the previous stat. That's actually having a binomial distribution with kn number of trials and the probability of success theta is a complete. So it's a complete sufficient statistic. You can refer, no? Ito, malalaman natin na complete sufficient statistic ito. You can refer to example 6.2.22 in the previous chapter. Or you can use the theorem. You can use the theorem 6.2.25. In this case, the binomial distribution belongs to the exponential family. Pwede natin ma-express niyan. Okay, an exponential family. And using the theorem 6.2.25, you can show that this summation of x sub I here is a complete sufficient statistic. Itong sa example 6.2.22, ito yung ginamit yung definition 6.2.21. Etong sa theorem 6.2.25, kung yung PDF belongs to an exponential family. Alam naman natin na yung binomial distribution belongs to an exponential family. So we can apply theorem 6.2.95. So yan yun, no? You can verify that it's a complete sufficient statistic. But no unbiased estimator based on it is immediately evident. Okay, so when in this situation, try for the simplest solution. We have the simple-minded estimator in this case. No? H of x sub 1 is equal to 1 if x sub 1 is equal to 1, and then 0 otherwise. Now, if x sub 1 is not equal to 1, then that will be equal to 0. Since we know that the possible values of the binomial random variable x sub 1, 0, 1, and so on and so forth up to how many trials? Nk. So, supposedly hanggang hanggang k lang pala kasi we refer it to x1 here. Ayan, hanggang k. Then 0 otherwise. So if we're going to determine the mean of h of x sub 1 here, the mean of x sub 1, so ano yung mean? So we have here the finite summation of h of x times the PMF. So ano yung PMF ng x1? Yan yung PMF ng x1 natin. So combination of k taken x1, so the probability of success, theta to the x1, probability of failure, 1 minus theta, k minus x1. Okay, so yan. Yung finite summation, i-evaluate natin yan, x sub 1, 0, up to k. Kung yung x sub 1 natin, 1, no? Kung x sub 1 natin dito, 1. So kaya h of x sub 1, 1 will be equal to 1. And all other terms of this finite summation will just be equal to 0 because of this defined function h of x1. Kunwari, h of x2. H of 2. Kung ang x1 natin equal to 2, so that would be 0. Kung x1 natin 0, h of 0, that will be 0. So maiiwan na lang yung h of 1. So h of 1 is 1. Para maiiwan na lang, no? Yung supposedly h of 0. And then we have the combination k taken 0. Then we have 0. Then 0. Theta to the 0. 0 naman yan. Yung first term niyan, no? Yung first term, isulat ko na lang muna yung first term natin. Yung second term natin, h of 1. So combination of k taken 1, theta to the 1, 1 minus theta, k minus 1. Okay? Other terms, plus h of 2, and so on and so forth hanggang h of k. 0 man ito sila lahat. So 0 yung mga term, 0, 0. So ito lang yung maiwan. That's why we have here, h of 1 is 1. Yan, dito yan, 1. So, combination of k taken 1, that is k. Theta to the 1, theta. Okay then. So meaning to say that h of x1 here is an unbiased, okay? It's an unbiased estimator of the function of the parameter. Ito kasi yung ating gusto natin i-estimate. Tau of theta equal to this. Yung expectation ng h1 equal to this. Pareho lang naman yan. Yung naka-highlight na orange dyan sa itaas. So, unbiased estimator, yung h of x1 of the function of the parameter. So this is the function of the parameter. So our theory now tells us, according to our theory, no? Sabi dito sa ating theory. Theorem pala. Theorem. T, alam natin na summation of xi is a complete sufficient statistic. And then let a function of our complete sufficient statistic be an estimator based only on this, then phi of t will be the unique best unbiased estimator of its expected value. So ang implication yan, the function of our complete sufficient statistic. Kaya ito yung complete sufficient statistic natin. The function of a complete sufficient statistic, ito yun sa ating theorem, T kasi ito, would be equal to, it is the best unbiased estimator of its expected value. That's according to our theorem. Equal to that. Okay, so according to our theorem, ito ngayon, ito siya, the phi of our the function of our complete sufficient statistic is the best unbiased estimator of the function of the parameter. Ito. Supposedly, kung gusto niyo siyang i-check without using the theorem, para ma-verify mo itong phi of t unbiased estimator, kailangan mo muna isolve yung expectation ng phi of t. Kung equal ba talaga siya sa function of the parameter theta. Yan yung sabi dito. Notice that we do not need to actually calculate the expectation of phi of t, but we conclude it to be the best unbiased estimator based on our theorem. Okay, so we know that it has a correct expected value by properties of iterated expectations. We must, however, be able to evaluate phi. Okay, we're going to evaluate our phi. Phi of t, actually, it refers to phi of t. We evaluate the phi of t. So suppose that we observe that the summation, yung summation ng xi 1 to n is equal to t, okay, t, because phi of t, this is the complete sufficient statistic. So kung ang value nito equal to t, ito yung kanyang estimate. So phi of t will just be equal to the expectation, the conditional expectation of h of x1 given the summation of xi equal to t. Check. Okay, so that's by definition above here. You have that phi of t. And then if we're going to determine the expectation of this, yung h of x1 is equal to 1 if x1 is equal to 1, and then 0 otherwise. Okay, 0 otherwise. So yung conditional expectation will just be equal to the probability of x1 equal to 1 given the summation of x sub I equal to t, because of the fact that h is 0 or 1. Kasi yung expectation supposedly, yung expectation supposedly 1 times, parang tayo, 1 times yung probability, yung h of 1, yung h of x1 equal to 0, and then the probability that x1 equal to 0, and then condition, then plus h of x1 equal to 1, and then times the probability, conditional probability ng summation. Kaya ito lang yung naiwan kasi 0 ito. Ito na lang yung maiwan apart. Because of this, h is 0 or 1. And then the conditional probability will be equal to this. This is true. We have the probability of the joint in our numerator divided by the probability, marginal probability of the summation of x sub I equal to t. And then since itong part na to, yung summation of x sub I from 1 up to n, that would this be equal to x1, okay? x1 plus the summation of xi, I from 2 up to n. Ito t man ito, equal to t. So, yung x1 natin, in this case, we consider it's equal to 1. So, that will just be equal to 1. This one is equal to 1. So, we have here the summation of xi, I from 2 to n will just be equal to t minus 1. Okay, yan. The probability of still of the joint, the joint probability over the marginal probability. Okay, x1 is redundant. And then since x1 is independent, we have a random sample, identically independent and identically distributed. So the joint will just be equal to the product of their probabilities, marginal probabilities. Okay, we have that. Alam natin na itong x1 binomial, k trials and probability of success is theta here. Ito is also binomial with k times n minus 1 trial with probability theta. And then the summation of xi is also has a binomial distribution with kn trials with parameter theta. So to compute phi of t, solve mo lang yung mga probabilities niya. Hindi ko na lang i-compute yan. So we have those probabilities, and then using your knowledge in algebra, simplifying all of this, then we have these results. So we have phi of t is equal to this. So this is a function. Estimate ito ng ating function of the complete sufficient statistic, phi of t. Estimate yan siya. So note that all of the thetas cancel. Natingnan natin dyan. It does not depend. No? Yung phi of t natin ngayon, it does not depend on the parameter theta. They must, because since the summation of x sub I is sufficient statistic. Kasi alam natin na sufficient statistic, it contains all the information about our unknown parameter theta. So nandun na lahat, kaya yung mga theta natin will cancel. Hence, the best unbiased estimator of this function of the parameter will be, kasi ito, estimate lang ito. Ito estimate. So phi of this complete sufficient statistic, summation of x sub I, will be equal to, okay, palitan na lang natin itong mga t natin dito. Yung mga t yan. By summation of the x sub i's. So it is the best unbiased estimator. So we can assert unbiasedness without performing the difficult evaluation of the expectation of this function of this complete sufficient statistic. Supposedly, no? Supposedly, kung gusto mo mag-assert ng unbiasedness, i-evaluate mo talaga yung mean of that estimator. So our estimator is a function of the complete sufficient statistic. Pero hindi na natin, we avoid this calculation and we just apply the theorem in which we have a complete. Yan. Pag alam natin na yung T, complete sufficient statistic, then this function of this complete sufficient statistic is the best of its expected value. Yan yung, kaya ito yung estimator of its expected value. Okay, so that's all for chapter 7. So next meeting, next week, I'm going to discuss chapter 8. Before interval estimation, point estimation man tayo. Ngayon, before interval estimation, we have the hypothesis testing. That's actually in chapter 8. So we're done with chapter 6 and chapter 7. I promise you to give you a problem set before. So hoping, no? This weekend, I'm going to send you the problem set. Send the problem set, and then one way of reviewing. And after the due date, I'm going to set the due date of the problem set. And after the due date of the problem set, the first exam follows. We have only 2 exams, chapter 6 and 7, and chapter 8 and 9. Okay, so any questions, any clarifications? So, taas-taas yung klase natin, ano?
Okay na sir, wala na kayo pumunta na sir.
Yung mga sinabi ko dito sa solution, yung iba pinakita ko talaga yung verification. Pero itong mga part na to, yung complete sufficient statistic, itong part na to dito, kung malalaman itong part dito. Yan. You try to answer that. If you're not sure about this, you try also. Why is it that the summation of x sub I has a binomial distribution with a kn trials and probability of success? Sir, pwede mo nga yung PDF na, sir. Yep, I'm going to give you the PDF for this. Apil na ning kwan na yung mga solutions na to. Para makayo. Okay, so I'm going to stop now the recording.